So today I wanted to go over a 2D equilibrium problem using unit vectors, and I feel that unit vectors are, uh, I guess, not the best way, but I guess a better way to learn about forces in more than one direction. Because once we start doing 3 dimensions and moments, we're gonna want to know about unit vectors. And unit vectors are a way to represent a direction, and that has a magnitude of 1. So, like on your x, y, z axes, you use the unit vectors I, j, and k hat. Here we're going to use these unit vectors to define the directions of the tensions on the rope TCA and TCB. And so what I've done here is I've drawn the free body diagram. TCA is in this direction, TCB is in this direction. The weight, of course, is down. And ECA and ECB are going to be in the same direction as TCA and TCB. So let's start by calculating what RCA is. So RCA is equal to XA minus XC, so 3 minus 6, which is in the I hat direction. I'm going to plus 5 and minus 0, that's YA minus YC in the J hat direction. So we're left with negative 3J, or negative 3I plus 5J. And now E hat CA is just, well, RCA over the magnitude of RCA, so negative 3I hat plus 5 J hat over square root of 34. So let's do that really quick on my calculator. Negative 3 plus, or sorry, no. So negative 3 over square root of 34, which is as a vector, which is going to be negative 0.514 I hat plus 5 over square root of 34, which is 0.857 J hat. We're going to do the same thing with RCB. So RCB is 7 minus 6 in the I hat direction, plus 5 minus 0 in the J hat direction, which is equal to 1 I hat plus 5 J hat. And so E hat CB is equal to 1 I hat plus 5 J hat over the square root of 26. So 1 over square root of 26, which is equal to 0.196 I hat plus 5 over square root of 26, which should be 0.981, 0.981 J hat. So now we're going to do our equilibrium equation, and let's change the color here. So this is our equilibrium equation: sum of the forces in the x direction, sum of the forces in the y direction, and sum of the forces in the z direction are all going to equal 0. And when we're dealing with moments, the sum of the moments is also going to be equal to 0. So let's start with sum of the forces in the x direction. Equals 0. So we have TCA times negative 0.514 plus TCB times 0.196. And this is going to be 0. So 0 equals that equation. Sum of the forces in the y is going to equal 0. Excuse me. We can't solve this equation just yet because we have 2 unknowns and only 1 equation. So we're going to use sum of the forces in the y to have another equation so we can solve for 2 unknowns. So we're going to have minus 100 for the weight of the block. I'm going to plus TCA times 0.857 plus TCB times 0.981. And there's many ways we can do this. I think the easiest way we can do this is just by substituting. So if we solve here for TCA, we're going to move TCA to the left hand side. So TCA equals TCB over, or times 0.196 over 0.58514. I'm going to substitute this in for TCA on this side. Minus 100 plus TCB times 0.196 over 0.514 times 0.857 plus TCB times 0.981. Okay, and this is equal to 0. So now we're going to solve. We have one equation, one unknown, so we can solve for TCB. And so we're going to move 100 to the right hand side, and then we're going to divide by the coefficient for TCB. So 100 equals 100, and we're going to add up these. So 0.981 plus 0.196 over 0.514 times 0.857. So we have 1.308 TCB is equal to 100. So TCB is equal to 100 divided by 1.308, 76.452 newtons. And this is the magnitude of TCB. If we wanted to have the direction components, we would just multiply this by E hat CB, because E hat CB has a magnitude of 1, so it would give us the components of TCB in the X and Y direction. So now we can solve for TCA. TCA is equal to TCB times this guy, so 76.52542 times 0.196 over 0.514, which is equal to 0.196 over 0.514 equals 29.153 newtons. And this is also a magnitude. If you wanted to get the components, you would multiply by E hat CA. So I hope you enjoyed this video. In my next few videos, I would like to do a 3D problem, which would be a lot more involved. But Hopefully this concept of using unit vectors to resolve to do equilibrium problems makes sense, because we're going to see them a lot more in the coming videos. Until next time, this has been great, and I hope to see you soon again. Bye-bye.